In this lesson, we are going to work on simplifying radical expressions using product and quotient properties of square roots, and this will prepare us to solve quadratic equations using radicals. So, let's review and practice. What we want to do is to simplify this expression, and when it is simplified, it no longer has any perfect squares under the radical, and also there cannot be a radical in the denominator of the fraction. The method that I'm going to use is called the factor tree or factored method. So what we're going to do is make a factor tree for 500, and any two factors will work. I'm going to use 50 times 10. And we want to get to our prime factorization, so this is 5 times 10. And since 5 is prime, we continue going with 10 as 2 times 5. And this 10 also will be 2 times 5. So we've created a factor tree down to our prime factorization. Now we're going to rewrite our radical, and under the radical we're going to list our factors in pairs. So I have 2 squared as my first pair, and then I have 5 squared as my second factor pair, and then I have a single 5 left over. Now what this does for us is then we can take the square root of each of these terms separately, and the square root of 2 squared is 2, because remember that a square root and a square are opposite operations, so they cancel each other. Or if you took 2 squared and got 4, you would know the square root of 4 is 2. The square root of 5 squared is 5, and then we will leave the square root of 5 because it can't be simplified any further. And then we multiply our two factors out front. 2 times 5 is 10. So our simplified version of the square root of 500 is 10 times the square root of 5. Now in letter B, we're going to use the product property, which says that we can multiply radicals together, and then we can multiply the numbers out front, or the coefficients, together. So the number out front of the root of 6 is 1, so 3 times 1 would be 3. And 12 times 6, both of those are radicals, so they can be multiplied together, and that would be 72. We're going to make a factor tree for 72, which would be 9 times 8. And then we continue simplifying. 9 would be 3 times 3. 8 as 2 times 4, and 2 times 2. So I'm going to rewrite the radical with my coefficient of a 3 and list my factor pairs. So I have 2 2's, which would be 2 squared. I have 2 3's, which would be 3 squared, and then I have a 2 by itself. So my 3 that I have out front, I'm going to leave. The square root of 2 squared is 2. The square root of 3 squared is 3, and I'm bringing these out as factors, so this will all be multiplication. And I can't simplify the square root of 2 any further. So I will multiply the coefficients together. 3 times 2 is 6, times 3 would be 18. So our final simplified answer would be 18 square roots of 2. When we are simplifying a fraction, which is a quotient, we can leave it as it is, or we can rewrite it as the root over the root and separate the two. Well, the square root of 25 is 5, and the square root of 3 can't be simplified. But I can't leave a radical in the denominator of a fraction. So the process to get rid of that radical is called rationalizing the denominator, and to do that we simply multiply it times itself. But if you do that in the denominator, you also must do it in the numerator. So our solution then would be 5 times the square root of 3 for the numerator, and in the denominator we'd have the square root of 3 times the square root of 3, which is the square root of 9. The square root of 9 is 3, and that rationalizing the denominator gets rid of the radical in the denominator. Letter D, we're going to separate our numerator and our denominator using the quotient property, which allows us to write the radical in each. Now, square root of 2 can't be simplified, nor can the square root of 11. So what we would have left to do is to rationalize the denominator, which we will multiply both the numerator and the denominator by the square root of 11. Using the quotient property, we can multiply these two radicals together. So the square root of 2 times the square root of 11 is the square root of 22. And if we were to make a factor tree for 22, it would be 2 times 11, so it can't be simplified any further. And then the square root of 11 times the square root of 11 is the square root of 121, which is 11. In other words, when you multiply any radical times itself, that means you're taking it squared. And remember, a square and a square root cancel, so you're just left with that number. Now, the reason we multiply both the numerator and the denominator is because, in effect, you're really multiplying a number over itself, which is 1. So when you're multiplying by 1, you're simply changing the appearance, which is simplified, but we are not changing the value of the original expression. Let's do a couple more examples. So the square root of 3 over the square root of 5. We're going to rewrite that using the quotient property, which states that we can rewrite the radicals separately. I can't simplify the square root of 3 nor the square root of 5, but I do want to rationalize the denominator. So I'm going to take the numerator and the denominator times the square root of 5. So I can use the product property, which means I can multiply the two radicals together, which gives me the square root of 15. And if I were to make a factor tree for 15, it would be 3 times 5, which can't be simplified any further. The square root of 5 times the square root of 5, or the square root of 5 squared, is simply 5. In our next example, we're going to multiply the square root of 5 times the square root of 8 using the product property, which gives us the square root of 40. So when we make a factor tree for 40 to simplify, we have 4 times 10, which is 2 times 2, and 2 times 5. So if I rewrite my radical using factor pairs, I'll have 2 squared times 2 times 5. The square root of 2 squared is 2, and then we have 2 and 5 left under the radical. And so that will be 2 times the square root of 10. The square root of 60, we're just going to simplify that. We're going to make a factor tree. That's going to be 6 times 10, 2 times 3, and 2 times 5. So we're going to rewrite the radical using our pairs. So I have 2 squared times 3 times 5. Remember that the square root of 2 squared is 2, and the 3 and the 5 are left under the radical, and since they are factors, we're going to multiply the two together, and we'll get the square root of 15. So the simplified version would be 2 square roots of 15. In our next example, we have the square root of 81 divided by the square root of 121. Right away, I recognize that the square root of 81 is 9, and the square root of 121 is 11. So this one simplifies right away. In our next example, we have the square root of 2 times the square root of 18. These are both radicals, so using our product property can be multiplied together. 2 times 18 is 36, and we know that the square root of 36 is 6. Some of you may have used perfect square method, and that's fine as well. I prefer using the prime factorization because it will also work when we get into cube roots and fourth roots. So let's review. We want to make sure that when we are doing simplified roots that they contain no perfect square factors. We want to perform the operations and then simplify, and please be sure that there are no radicals in the denominator. Please complete the reflection.